My name is Ali, and I will be giving you an introduction to modulation on behalf of Group 17. Modulation is the process of converting data into radio waves. It is used to transmit signals over a distance, and this is done by using the baseband and carrier signal. The baseband signal, also known as the message or modulating signal, holds the message that we want to transmit. And the carrier signal is a wave with a steady frequency. The baseband signal is imposed on the carrier signal, and the carrier signal is then transmitted. The process of imposing the baseband signal onto the carrier is like hiding a code inside the carrier wave. Modulation is very important. It helps reduce antenna size, reduces interference, and allows different signals to be transmitted simultaneously. The types of modulation used depend on which element of the carrier signal we change. This means that if we are hiding the message via the amplitude, we would be doing amplitude modulation. There are two broad categories of modulation: analog and digital. We will be focusing on the analog portion, specifically amplitude modulation, which falls under the continuous wave modulation subset. Amplitude modulation changes the amplitude of the carrier signal in accordance to the baseband signal. The M of t equation represents the baseband signal. The C of t equation represents the carrier signal, and the equation for the amplitude modulated wave is given by S of t. We can see that the amplitude modulated wave is made from the baseband and carrier signal because the equation S of t is a combination of M of t and C of t. A characteristic of an amplitude modulated signal is the modulation index. It can be found by dividing the amplitude of the modulated signal by the amplitude of the carrier signal. If the modulation index is above 1, then the signal is overmodulated. If it's under 1, then the signal is undermodulated. And when it's exactly 1, it's perfectly modulated. If overmodulation does occur, the signal is chopped up, and we can see from the image the envelope of the output waveform is distorted. Therefore, the modulation no longer resembles its modulating signal, and the signal will be very distorted and unreadable. Overmodulated signals will have an increased bandwidth and will have unwanted harmonics mixed in them. When we are modulating, we need to make sure that we do not overmodulate the signal. The bandwidth of an amplitude modulated signal is the difference between the highest and lowest frequencies. The max frequency of an amplitude modulated signal can be found by adding the carrier frequency and the modulating frequency, and the minimum frequency can be found by subtracting the modulating frequency from the carrier frequency. The bandwidth of an amplitude modulated signal is twice the modulating frequency. All amplitude modulated signals have power, and it can be found by using the normalized average power equation. The power in the carrier component is considered wasted power and is denoted by PC. The power in the sidebands is the useful power, and it's denoted by PM. Since we know from the previous slides that the carrier component is the wasted power and the power in the sidebands is the useful power, we can find the modulation efficiency by dividing the useful power by the total power. When doing this, we have to make sure that the signal is undermodulated or perfectly modulated. This is denoted by the modulation index being less than or equal to 1. Double sideband suppressed carrier modulation aims to fix some of the shortcomings of regular amplitude modulation, specifically the power wasted on transmitting the carrier signal. For normal amplitude modulation, the efficiency is limited to 50% at max, and the efficiency is much lower in practice. The way double sideband suppressed carrier modulation fixes these shortcomings is by dropping the power wasting term, which deals with the carrier component. Double sideband suppressed carrier modulation can be represented by the following equation that is listed on the slide. Double sideband suppressed carrier modulation is 100% efficient since no power is being wasted on the carrier signal component and all the power is being used to transmit the two information carrying sidebands. However, this efficiency comes at a cost. In order to demodulate a double sideband suppressed signal, the receiver will need the carrier frequency and phase in perfect synchronization with the original carrier that was used in creating the signal. This process is called coherent demodulation. Single sideband modulation is a form of amplitude modulation. It is created by removing some of the components of an amplitude modulated signal. Specifically, the carrier is removed, like with double sideband suppressed carrier modulation. But the thing that separates it is that instead of having two sidebands, we now only have one. This works since both sidebands are just mirror images of each other. The reason for creating single sideband modulation and double sideband suppressed carrier modulation is because amplitude modulation has big downfalls. It occupies twice the bandwidth of the modulating signal, and it is inefficient in terms of power because it transmits a power wasting carrier signal component.